Alright guys, it's me again. Today what I'm going to do is I'm going to give you guys a little bit of homework help by doing a problem that's very similar to the problems on homework 2. Alright, so for number 4 it says Roadrunner accelerates at a constant rate as he travels 10 meters along a straight track from point A to point B. If his speed was 4 meters per second at point A and will be 6 meters per second at point B, how long will it take for him to get from point A to point B? So the way we're going to do this, we're going to change around the problem a little question. But let's do this. Okay, so let's suppose Roadrunner instead travels, let's have him go 20 meters. Does that sound fair? So let's have this be 0 meters and this is 20 meters. Okay, and this is point A and this is point B. All right, we'll even put a point there. That way it's very clearly a point. Awesome. Now let's suppose his speed at point A. So this is going to be my Roadrunner. Yeah, okay. He's going at 4 meters per second initially. And then at the end, okay, he's going, we'll make this 8 meters per second. We're going to just change around the problem a little bit. So he's running really fast. Okay, this is Mr. Roadrunner here. We got going there. That's right. And now he's going 8 meters per second. Okay, this is different than the homework, different numbers. So we want to know how long will it take to get him from point A to point B. So we want to know time from A to B. All right. So what we're going to start off is making a what I like to call knowns corner, which is just kind of what you do is you start off by telling us what we know and what it is that we want to find out. So let's start with acceleration. Do we know the acceleration? No, but we know that he accelerates at a constant rate. Now that's important. That means that we can use our kinematic equations. So A is constant. Awesome. Now what do we know about velocity? Well, we know his initial velocity, is 4 meters per second. And we know his final velocity, right? So this is his initial, this is his final. At the end of the story, it's 8 meters per second. All right? Now, what about the distance that he's traveled? Well, the initial position that he's at is going to be at 0 meters. And the final position, x final, is going to be 20 meters. All right, so we're in business and we want to know time. Okay? So let's bring down our kinematic equations, all right? The ones that we want to use. I'm going to use, really you could choose to do it differently. But I like the top two because they're my favorites. There's no square. They're not as icky to me as the other ones. So we know by definition, right, acceleration is equal to the change in velocity over the change in time. And this already basically gives us our first kinematic equation because that's just the same thing as saying the final velocity minus the initial velocity, right? That's how much your velocity changed over the time that it took to do that, right? Which really means that your final velocity, now we're just going to rearrange this, you could really do it yourself, is equal to velocity initial plus AT. And the way that you get that is by taking this T and you multiply it on both sides, so you get an AT over here, and then you add the initial. Go ahead and do it on your own paper and you'll see that that's what we get. Okay? Now our other kinematic equation, which I believe I proved in a different video that you guys should also take a look at, is just that the change in position is equal to the initial velocity times t plus 1/2 acceleration times time squared. Okay, now of course the change in position is just the final position minus the initial position. So as a rule in physics, we don't plug in numbers until we absolutely have to. We like using letters until the very end, just because, I don't know, I guess it gets less confusing, and as you get more and more advanced, you're going to see how this gets really useful. So don't touch any of these values, just know that we have them, okay? Only at the very end do you need to plug them in. By the way, if you do every single thing in one of your homework assignments and you just forget to even plug in numbers and you give me an answer in symbols, I'll still be pretty happy. You will get the vast majority of the points. So the point here is not the number at the end, but your process of doing it, all right? So please remember that. That being said, we have velocity initial, so we can plug in for this, and we can plug in for the final velocity, and we can plug in for the change in position. What we can't plug in for as a number is the acceleration. All we know about the acceleration is that it's a constant, which means we can use these in the first place. So we're going to say acceleration is an unknown, all right? Let's make sure you can see. Excuse me. can't spell tonight. It's very late at night. It's almost 2 in the morning, but that's when Miss Mizrachi does her grading. So that's when Miss Mizrachi is going to make this video for you. So your acceleration is unknown, but it's a constant. All right. Now your time, well, that's what we're trying to find out. So the time is what we want also. So that's also an unknown. Okay. So we have two variables, acceleration and time, and two equations. Well, we can solve this. And since we want to solve for time, I suggest we substitute in for acceleration. This will make a lot more sense later as the semester goes, but I promise very soon, before you think, you're going to get such an intuition for this, it's unbelievable. So we're going to start off by solving for the acceleration. Well, we actually had it to start with, right? We know acceleration is the final velocity minus the initial velocity divided by time. So if we plug in for the acceleration here, what are we going to get? We're going to get the change in position is equal to the initial velocity times time plus 1/2 acceleration, which for the acceleration we're going to plug in this. So we get v final minus v initial over time, all right, times t squared. You see how this is getting very, very cool? This isn't so bad anymore, is it? We're going to now go ahead and cancel these t's because why not? We can. So that means that this is all of a sudden v initial times t plus v final minus v initial over 2 times t, which is, we're going to spread it out and solve it. So we get v initial times t plus 1/2 of v final times t minus 1/2 of v initial times t. See how that works? So what we're going to do now is just put it all together. So notice that 1 v initial minus 1/2 of a v initial is another 1/2 of v initial. Does that make sense? So if I have a whole pie and I take away 1/2 of a pie, then I get 1/2 of a pie. So if I have a whole velocity initial minus 1/2 of a velocity initial, I'm going to get left with 1/2 of a velocity initial. So that means that this equals 1/2 velocity initial times t plus 1/2 velocity final times t, right? And all that, of course, is still equal to the change in position, okay? Now notice this is very easy to clean up because that means that the change in position is equal to 1/2 v initial plus v final times t. Isn't that nice? Okay, so now what we're going to do over here is we're going to solve for t. I just want you to stop for a second and see how this works. Do you see how very, very simple this is? And by the way, this has tremendous, tremendous, tremendous implications because what we just did was prove a very interesting fundamental theorem, okay? And that's that the average velocity is equal to the total change in position over the total change in time, right? Because if you notice, if we divide time from both sides, we get the change in position over the change in time is equal to the initial velocity plus the final velocity divided by 2. Okay, now this is always true, and this is assuming constant acceleration. And it's very, very cool that we just figured that out backwards, okay? But of course, what we're trying to solve for here is time. So this is not what we want to do, even though it is true, okay? So now we want to solve for this time. Okay, I'm going to go ahead and take a new sheet of paper so everybody can see what's going on. So we left off with the change in position is equal to 1/2 the initial velocity plus the final velocity times the time that passed. So if we solve for this t, we get t equals, multiply both sides by 2 delta x, and we're going to divide both sides by this part here, divided by velocity initial plus velocity final. Okay, does everybody see how that works? So I'm just going to go ahead and just do that one more time just to show everybody very clearly how that happened. So we're going to multiply both sides by 2, right? Right, so then this obviously goes away, and we get, well, it's actually not so obvious, but we're going to pretend it's obvious because we're physicists. 2 delta x equals velocity initial plus velocity final times t. Now we're going to multiply both sides by velocity initial plus velocity final. All right, and then we get 2, I'm sorry, divide by, I apologize, divide by. And then we get 2 divided by velocity initial plus velocity final times delta x equals time. Isn't that lovely? So now that we have an awesome, awesome equation, what we're going to do is we're going to go ahead and plug in numbers, all right? So what do we have? We have 2, right? We have change in position, which is our delta x, which is just 20 meters, okay? Then we have our initial velocity, which is 4 meters per second. And then we have our final velocity, which is 8 meters per second. Okay, and that's going to equal the total time. By the way, as an extra check, we're going to make sure that the units line up. That means at the end of the day, we should end up with seconds, right? Because time's measured in seconds, no meters. So 2 times 20 is 40, so we get 40 meters up top. And on bottom, we have 4 meters per second plus 8 meters per second is just 12 meters per second. Okay. Now we're going to simplify this a bit. I'm just going to go ahead and do it like my own way. And that is, I'm going to divide both by 4, so I'm going to get 10 thirds. Do you see how that works? And then I have meters divided by meters per second. Okay. Now remember, when I divide a number by a fraction, what I really do is I'm just going to take the units down here. So this becomes meters times, I flip the fraction on the bottom, seconds over meters. These cancel out, and I just get seconds, which is exactly what I want. Isn't that beautiful? So the time passed is 10 thirds seconds. Isn't that awesome? It's very, very cool and really not so hard. So, and this is going to be about like 3.33 seconds, which if you think about it, makes a lot of sense. I guess, you know, Mickey Mouse likes to accelerate. So I hope this was helpful. Please, please, please take this and practice it and memorize it and utilize it. And I will see you in class. Good luck.